Okay, so let's verify the result of the app, Science Journal app. Science Journal app, specifically for the accelerometer feature. Okay, so I've used this app uh, and installed this in the pVolts shaking table, wherein the intensity at intensity 5 say to 8. Okay, shaking table with intensity 5 to 8. Okay, according to a resource person from pVolts, uh, we do not need to test the shaking table they have there from intensity 1 to 4 because it's not really felt by humans, right? Uh, Thus, the shaking table they have there is capable of generating an intensity 5 to 8. Okay. While while tested with the shaking table, I installed or attached the mobile phone with the accelerometer feature of the Science Journal app. Okay, and it was able to generate recordings. Okay, so that recordings is in a form of accelerogram versus time. So, for example, uh, on the first few seconds, without intensity less than intensity 5, the accelerometer recording could be something like this. And then when intensity 5 comes, it will rise up unto this point, intensity 6, and then 7, and 8, then so on, and until it fades. So that's the trend of the readings. The higher the acceleration reading, that means the intensity increases. Okay. Now this accelerometer or acceleration versus time recordings can be converted into displacement reading. Okay. But how? Okay. Insert new page. Okay. So what I did is, after getting the recordings from the shaking table, I post-processed the recordings of this one, and post-processed that in Excel or spreadsheet to get the displacement. Okay. Remember that acceleration in mathematics is equal to the derivatives of velocity versus time. Okay? While velocity is in calculus is actually the derivatives of x or distance with respect to time. Okay? That means, so this is a differential calculus problem. Therefore, if I have acceleration which is dv dt, if I integrate that, I'll be getting my velocity, right? And then if I have velocity which is dx dt, if I integrate that, I'll be getting my x, or displacement. Okay. How do we get the integral of dv dt, or the acceleration? Remember that if I magnify this graph, it could be something like this. I'll change my marker, something like this, right? And then that is acceleration versus time. I have reading here, I have reading here, and and this time is in seconds, right? Seconds. So say this is 9 meter per second square, and this is 8 meter per second square. Okay. In integral, we are actually getting what? We are getting the area. Okay. We're getting the area. That means simply get the area of this one to get the corresponding velocity. So velocity is equal to area of this. Area of acceleration time graph. With that analogy also, therefore, the displacement is equal also to the area of velocity and time graph. Okay. So, how do we get, okay, select all. Okay, how do we get the area? So, I'll delete this first. How do we get the area of that? You simply have to use the Simpson's formula, or the more simpler one is trapezoidal method. Okay. In this exercise, trapezoidal method is for me good enough because the increment of the readings in the app is about point milliseconds. So that's how accurate it is, right? So it's just fair enough to use trapezoidal method. So in trapezoid, what's the area of trapezoid? It's simply area is equal to 1/2, say D1, this is D2, and this is B. So D1 plus D2 times B. So that's it. Okay. Therefore, in this situation, our area is 1/2 times 9 plus 8. And how do we get B, or the seconds here? Simply subtract the uh, how do I name this? This is, say, time 2 minus time 1. Okay, so time 2 minus time 1, which is given in the readings of the app. And that means you can now get the area, then you will now be able to get the velocity. So velocity is now determined from the acceleration versus time graph. Now, once you have the velocity, you can now come up with a velocity and time graph, right? and I'll show you later. And then simply do this again, find the area of the velocity time graph, and that means you get now the displacement. Okay, so for example, I'll be playing a video wherein here, okay, I tried to calibrate or say verify the readings of the app. Okay, for example, here, so I set up a ruler. I made a marker on the ruler, on the paper. That means my origin will be here. Okay, so the acceleration could either be here, or going here, from going to the right or going to the left. Uh, this should be right, this should be left. Okay, so I shake the mobile phone on that direction, and it will measure the acceleration. And then I made sure that the mobile phone will just be touching these uh, two marker, which is about, this is 10 mm each, so that will be only 20 mm. Okay, but my actual shaking with this does not exceed this two. Okay, therefore my reading could only be on the range of 10 mm. Okay, or so. Okay, but definitely less than 20 mm. So I'll show you here. And so I'm showing how I place the marker with my guide of the ruler. Then I place the center of the mobile phone to my origin. Then I shake the phone so that it records an acceleration versus time graph. Okay. There are lots of tutorial in Google or YouTube how to send the recordings in email. So you just have to, after recording, you just have to simply click here, and there's an option like share. If you are connected to a Wi-Fi, once you click the share, there's an option of email. So if you email that, the file is automatically in a CSV file, which is readable in Excel or spreadsheet. Okay, and then I'll show you the corresponding file of that. Okay, so that's it. Okay, so uh, once you email that, okay, not this. Okay, so as you can see, so this is the actual recordings of the app once emailed. Okay, so you have the relative time and the corresponding acceleration in next direction. So you need to post-process this. Okay, so to do that, uh, I post-process that. Okay, so this is the actual recording. Once you share the reading via email and download it, okay, it's a CSV file, so you have to save this first as an Excel workbook. So I'll save this, then click on no, so that you can, oops, so that you can set that into an Excel workbook. Okay, so say try, okay, then save. Okay, so remember this is in meter per seconds. So how do I post process this? For example, this is acceleration, right? So to get the area of that, the area of acceleration time is velocity, right? So I'll type in velocity here, then do the trapezoidal formula. So equals 0.5 times the readings, this plus this, multiplied by the time increment. So this is your time increment, this 2. That means this is 61 milliseconds. So from 0 to 61 milliseconds, you have this time increment. So therefore, 61 minus 0, right? But since that should be millisecond, I'll divide that by 1000. Okay? So to convert into seconds. So open parenthesis, this minus this, and all over 1000. Okay, so that is now in, the velocity is now in meter per seconds. Okay, then simply drag it down, drag the cell to copy the formula and all the way down to here, and then paste. Okay, okay. Although in this last reading, I might ignore that because that's maybe since that is the last reading, it could produce a blunder or an unacceptable area. Okay. By the way, if you want to plot the acceleration versus time graph, so simply select the two columns. Okay, here, select that, and in Excel, click on Insert, Charts, and Scattered Plot. Okay, and that's your reading already. That's the acceleration versus time graph. As you notice, your maximum acceleration occurs at about 8 seconds, right? Okay. Now, remember this is an acceleration versus time. Change this, acceleration time graph. How about the velocity time graph? So you just have to copy this. Where's that? Oops.
First day mo, pwedeng hindi Bye.
Okay, so to get the velocity time graph, so simply insert, do another chart. So just right click, select data, okay, and then add. Then for the x value, we all know that the x should be the time. So up until here, then enter, and then for the y, it's the velocity from here all the way here. But I believe this one is a since this is a last reading from the trapezoidal formula, maybe I'll ignore that, and then okay. So we're now looking at the velocity time graph. Okay, then title is velocity time graph. So again, if you integrate the velocity, which is dx dt, you'll be getting the displacement, right? So simply apply the trapezoidal formula like here, and then insert another column, say displacement. So that will be, copy this, Control C, Control V, but I'll change this one plus this, and then this minus this. Okay, and then Control C. Oops, wait. No, sorry. So this should be this plus this, then Control C all the way down. Since I ignored this, I'll be ignoring that also. Okay, so let's now insert another graph for displacement time graph. Okay, so I'll insert another graph. Insert. Okay, so and then right click, select data, add. So for the x, again, that is the time. Okay, and then enter. While for the y, it's now the displacement. This up to here, enter. Okay. 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 So as you notice, there's a blunder here over there. The last reading again. Okay. If you notice, the maximum displacement occurs midway, right? Midway in the experiment, which is about that is 0.007. Okay, but the maximum velocity also occurs midway, almost midway. That it's, but the acceleration occurs about 8 seconds. So it doesn't necessarily mean that once acceleration, that your maximum acceleration will give the maximum displacement. So that's the idea here. So it doesn't necessarily mean about that condition, because in here, based on this graph, our maximum displacement occurs midway, but the maximum acceleration occurs about 8 seconds. Midway here is about 5 seconds. Okay. Now, what's the maximum displacement? According here, it's 0.0007 meters. So how do you easily find that out? So simply type in max or mean, right? So get the max here, which is this, then close parenthesis, enter. That's it. And simply, since that is in meter, to get that in mm, simply multiply that by 1000. So I'm getting 7 mm. Okay, remember my setup here, I told you, I only shake the mobile phone, not touching both the 10 mm marker. So that justifies that my measurement in this experiment is almost the same with what I have got from this data. Okay, so I wish you do the same on your experiment. You come up with the same with your reading and with your reading in the ruler, and theoretically using numerical methods like this. This is a numerical methods approach because we were able to find the velocity and the displacement by trapezoidal method, and considering the time interval, which is in milliseconds. Okay, so I wish you learns a lot here. This is important because remember the idea of putting in accelerometer in the building is once you have the once you have the corresponding accelerometer, say, oops, can't. say if you have, why can I write? Lang. So if you have a building and then you put in accelerometer, okay, and then that accelerometer, we're able to generate this one by the numerical methods approach I told you, you will be able to get the displacement, right? So in short, once you have a certain earthquake happened in the building, you will be able to calculate the corresponding displacement of your structure, which is very important. Because remember, in stiffness method, if you know the displacement and then you know the loading is actually this, you will be able to get the stiffness, okay? Stiffness of structure. If you happen to know the stiffness of the structure by just getting the displacement, you will be able to learn to know if your structure is still safe for another earthquake, say a magnitude 7 earthquake. So that's the importance of having an accelerometer inside the building in the ground to measure the ground displacement, and in the floor of a structure to measure the displacement at the top. Okay, if you determine the displacement at the top, you'll be able to get the stiffness of the structure, which later on determines if your structure is still safe. Okay, so that's it. How about in my P volts reading? Okay, so here I've tested the app in the P volts shaking table and find out the accelerometer or the acceleration time graph, and then later on converted the displacement. So I'll let you think what maximum displacement did I get for that. Okay, so as you will see, the table generates intensity 5 to 8 or 6 to 8. Actually, for intensity 8, it's already so intense that I almost fell down on the floor. So, and then, but I was able only to capture the displacement on the floor. Okay, so I'm sitting there on top of the platform. It's now shaking. You will see from time to time I'll be switching the video to the corresponding intensity. See, so that's intensity 6 and 8. I think 8.4 is the gale. So as you see, the app reading is on this displacement, right? So you can now imagine uh, the video is now shaking because I can't stabilize my position. I need to hold on some hand handheld bar over the house. That's a mini house actually. So there's a door beside me. So that's intensity 7 as you see, and that's intensity 8. That's already intensity 8. You will see that I'll be moving outside the house because I can't stand on it.
So yung pinakamalakas kanina, 8 po. Mm, ang sa scale po natin, di ba po ba 10? Hindi, may 10 tayo pero hindi ito nangyayari pa sa atin. Kasi pag nangyari yung 10, ang equivalent pa yung almost mas talaga eh. Halos wala na makatayong building yun pag natin. So, ang realistic hanggang 8 po. 8 po. Hindi, pinakamalakas na intensity.
Yeah, so realistic is 8. So just imagine for intensity 8, I almost felt dizzy. I cannot stand on the platform already. So if it happens in the actual earthquake, I felt down on the ground for sure.
Sige, patuloy natin. Ayun eh. Ang max ko, 9.4 meter per second square.
So you are now seeing the actual recording, so which is my max is 9.4 meter per second square. I'll show you the actual CSV file later on.
Okay. So, ano po yung intensity 8 po? Okay. So,
Okay. Okay, so this is now the post-process reading of the video earlier. So as you see, I also got the 9.4 meter per second square maximum. And my minimum is negative 11 meter per second square. And then post-processing that, getting the velocity and the displacement. According here, I got about 400 mm displacement. So with that checking, I felt, so that corresponds to 400 mm. Okay, displacement. Okay. So with that, I think you should try that also on your own. So I wish you'll be able to get the same displacement from the acceleration time graph that you generate, and definitely you have to find a way to measure your displacement. You can copy what I did earlier by just placing a marker from the ruler, then shake your mobile phone to a specified, no? You will dictate, no? You will dictate how much it will displace, and then you should come up with the same displacement after post-processing in Excel. And with the importance, for the importance of that of that exercise, so this is the importance. You will be able to determine the safety, the health of the structure just by determining the displacement over time. So take note, this is a continuous reading because earthquake comes on a time of the day or a time of a night that we do not know. So therefore, your accelerometer should be placed on the structure 24/7, so that it can measure the displacement anytime earthquake happens. Okay, and as an engineer, it's best that you can monitor the life of your structure 24/7 because it determines if your structure is still safe. Okay, if your structure changes displacement over time, from a specified earthquake ground motion, that means some portion of your structure might be damaged. So that's the time, that's the signal for you as an engineer to find out where the damage is, how, and then apply the proper retrofitting or rehabilitation. Okay, so that's the importance of this exercise.